the universe. From the glowing wisps of nebula to the shine of newborn stars, from blazing galaxies to the warm embrace of our own sun, the universe has dazzled humanity for all time with its brilliance. However, the universe is mostly space, and that space is cold, very cold. But that doesn't mean there isn't anything to see. When observed in a special way, even cold things glow. Like these strangely colored blobs, they aren't exotic cosmic objects at all, nor will they ever fill a room with their light. Even these ice cubes emit radiation we can detect, infrared radiation. Infrared radiation is created by the motion of atoms and molecules that are in matter. So even objects that we think of as being very cold, such as ice cubes, emit radiation. Like ice cubes, the coldest things in space emit radiation. And with special instruments, we can detect this radiation to reveal a dazzling universe of unseen wonders. Legions of galaxies, and what lies within their cores. The secrets of seemingly empty space. The birthplace of stars. And even the birthplace of planets. Planets like ours. How do we see these things? With the Spitzer Space Telescope, the last of the 4 great observatories. Spitzer's greatness is not due to its size. With a mirror less than 3 feet across, it is easily dwarfed by the other great observatories, Hubble and Chandra. But despite its modest stature, Spitzer's infrared observations are 1,000 times more sensitive than any ever made. That's because it does its work in the frigid depths of space. Positioned in a unique orbit, 1,000,000 miles distant, Spitzer trails the Earth like a lone sentinel, following us as we journey around the Sun. Here, in the deep freeze of space, Spitzer is far from anything that would interfere with its infrared vision. By gazing into the distant reaches of space-time, or perhaps somewhere nearby in our own galaxy, photons are gathered by Spitzer's mirror. From here, the photons can be directed to different instruments that are frozen in liquid helium so they don't emit infrared radiation that would interfere with the observations. With a photometer, spectrometer, and cameras, observers can count, characterize, and make images with the infrared energy from sources, allowing us to see what has never been known. They can see stars that are invisible to our vision. They can sense vast, invisible clouds of matter and reveal what they're made of. They can reveal dust around stars, dust that is forming planets like ours. And they can detect galaxies in the deepest reaches of space-time.
Main engine start and liftoff of the Delta II.
Launched in August of 2003, Spitzer has completed its primary mission: to establish a legacy of new information about our universe, the Spitzer legacy. How do stars form? What causes them to form? How do solar systems form? Do all stars have solar systems? Are there any solar systems like ours? Are there many? Are there few? What does our galaxy really look like? Are new stars forming in our galaxy? Where? Why did galaxies form? Were the first galaxies like our galaxy? Why are galaxies where they are? How did the structure of the universe form? These are questions that the Spitzer Legacy Program is designed to address. Using Spitzer's unprecedented infrared vision, 6 programs focused on different aspects to fill gaps in our knowledge. 2 Spitzer Legacy programs, SINGS and GLIMPS, focused close to home to understand our own galaxy and those in our cosmic neighborhood.
SINGS stands for Spitzer Infrared Nearby Galaxies Survey. And the idea of the survey is really to broadly sample the local population to get a census that is representative of all of the types that are found today in the universe, and also provide type examples for the kinds of things that surveys like SWIRE will see in the distant universe. Ours is actually a survey, as the name implies, nearby galaxies. They're within distances of about 100 million light years of the Milky Way. What that really means is our galactic neighborhood, galaxies within a local supercluster, and it includes a lot of the kinds of famous galaxies that many amateur astronomers will look at in their backyards. For example, the Whirlpool galaxy, M51. The advantage of looking at galaxies nearby is that we can actually make images and study in great detail the galaxies. In fact, many of the images that we're obtaining are some of the most beautiful images Spitzer is obtaining. In addition to effectively photographing the galaxies with the MIPS and IRAC instruments, we're also mapping the galaxies using the spectrometer on Spitzer, the IRS instrument. What those maps do provide us is physical information about the physical conditions in the star-forming regions. Things like the temperatures of the gas, the pressure of the gas, the motions of the gas. And this allows us to obtain hard numbers on the properties of the star-forming regions, and really allows us to pull that much more information out of the photographs and images that we obtain. The Whirlpool galaxy M51 provides an excellent example of the power of these infrared observations. If you look at an optical image, in other words, one made in visible light, you can see knots of star formation that are in the visible. You also see the image crisscrossed with dark lanes, dark features. These are dust lanes, clouds of gas and dust. And in truth, the stars really are being born at this time in those dark lanes, but most of that star formation is nearly utterly invisible to us from the ground because that dust is obscuring those regions. It's the same gas and dust that is giving birth to the stars also provides a cloak that hides those regions from us. Now, if you look at the same galaxy in the Spitzer images, you in fact see that what were dark lanes in the visible image are now bright. That Spitzer actually is measuring the light from that dust, and suddenly you can see a series of knots of these truly newly born stars that were not visible in the optical photograph. Of course, neither of these pictures is complete, but by combining the view from the visible with the view from the infrared, we get a complete picture of the star formation. And this is something that Spitzer is doing for the first time. It is not the first telescope to study galaxies like the Whirlpool in the infrared, but it has unprecedented ability to make sharp images of these galaxies in the part of the infrared spectrum where most of these young stars are producing their light.
Using these capabilities as they were used in the SINGS survey, Spitzer not only provides volumes of important new data, it has revealed amazing new views of our neighboring galaxies. In these views of our nearest galactic neighbor, the Andromeda Galaxy, we finally see the extent and amount of dust in the galaxy and captivating new features, including bright, aging stars and a spiral arc in the center of the galaxy. The infrared image also reveals an off-center ring of star formation and a hole in the galaxy's disk of spiral arms. The galaxy's central bulge glows in the light emitted by warm dust from old giant stars. Just outside the bulge, a system of inner spiral arms can be seen, and outside this, the prominent ring of star formation. When combined with the visible light image, we see a new vista of the Andromeda Galaxy's complexity and beauty. Further away in the Big Dipper, Spitzer viewed the galaxy M82, previously known to host a hotbed of young, massive stars. The new Spitzer image reveals for the first time the smoke surrounding those stellar fires. The huge red clouds are actually dust believed to contain a compound similar to car exhaust. The smelly material called polycyclic aromatic hydrocarbons can be found on Earth in barbecue pits and other places where burning has occurred. In galaxies, the stuff is created by stars whose winds and radiation blow the material out into space. These hazy clouds are some of the biggest ever seen around a galaxy. They stretch 20,000 light-years away from the galaxy in both directions, far beyond where stars are found. Farther away in Canis Major, two merging galaxies have caused dusty clouds to form into dense regions of star formation. Seen in visible light in this Hubble image, the clouds are invisible, but for the first time, Spitzer reveals them in infrared light. Hot young stars forming in the dusty knots heat the dust, which then radiates in infrared. Combining the two views shows us a more complete view of the processes occurring in this cosmic collision, and also provides a beautiful new perspective on our cosmos. Glimpse looked even closer to home and promises to deliver much more than its name implies.
The anagram itself is the Galactic Infrared Mid-Plane Survey Extraordinaire, and we believe, in fact, that it is extraordinary in the sense that we're seeing an entirely new view of our galaxy that really nobody has seen before.
This first look that Glimpse took sees all the way to the far side of the galaxy. Except for a few bright stars, nothing in this picture can be seen in visible light. It would be darkness. But with Spitzer, our galaxy is revealed anew. It shows millions more stars than we've seen before in any light, but it is still less than 10% of what Glimpse looks at. This tiny sliver of that vision contains a treasure trove of new objects and volumes of information about our Milky Way.
We see a whole range of different kinds of objects. We're also uncovering many, many more stars than essentially any other survey has done for this particular area. We've uncovered something like 50 million stars that will be cataloged. So we're seeing about 50 times more stars per unit area.
And what is revealed? Red clouds, illuminated by stars forming nearby, indicate the presence of large organic molecules mixed with dust. Patches of black are dense, obscuring clouds of dust, impenetrable by even Spitzer's super-sensitive infrared eyes. Bright arcs of white throughout the image are massive stellar incubators. Zooming in, we see bubbles or holes in the red clouds formed by powerful outflows from massive groups of forming stars. Wisps of green indicate the presence of hot hydrogen gas. Star clusters can also be seen as groupings of blue, yellow, and green specks inside some of the star-forming clouds. In addition to all the stellar birth in this image, Spitzer also sees a planetary nebula, the final gasp of a star like our Sun, whose outer layers are blown into space, leaving behind a burnt-out core called a white dwarf. In its search to detect other invisible wonders deep within our galaxy, GLIMPSE revealed a never-before-seen globular cluster. Where visible images show a typical field of stars, this GLIMPSE image reveals a cluster of ancient stars, 10 to 13 billion years old, that date from the very beginning of the Milky Way. Like fossils, these tightly packed knots of stars are among the oldest objects in our galaxy, each containing several 100,000 stars, most of which are older and less massive than our Sun. There are about 150 known clusters like this orbiting the center of the Milky Way, and these ancient remnants provide important information about the evolution of our galaxy. Perhaps the single most surprising revelation was about the form of our own Milky Way, which was made possible by the overwhelming number of new stars visible to GLIMPSE. Like mapping a forest by standing in it, the GLIMPSE astronomers cut through obscuring clouds of interstellar dust to gather infrared light from tens of millions of stars at the center of the galaxy. This produced the most comprehensive structural analysis of our galaxy and revealed a central bar, roughly 27,000 light-years in length, spanning the center of the galaxy. They also found that it is oriented at about a 45-degree angle relative to a line from the Earth to the center of the galaxy. It has long been theorized that the Milky Way may be a barred spiral galaxy, and by providing the most detailed picture to date of the inner regions of our galaxy, GLIMPSE has produced the best evidence that it is a barred spiral galaxy. Not only has Spitzer revealed the form of our galaxy in the GLIMPSE survey, in other observations, the same ability to reveal the invisible has unveiled the Milky Way like never before. In visible light, this view cannot be seen. Obscured by dust, it would appear dark. But here, at the center of our galaxy, Spitzer reveals throngs of old stars amid fantastically detailed clouds of glowing dust lit up by younger, massive stars. And at the brightest spot in this image, the very heart of our galaxy. Looking at these immense clouds, clouds of hydrocarbons heated by hot stars, we can see a bright spot. Looking closer, and with more detail than ever before in infrared, we can see the disk of material surrounding the black hole at the very heart of our Milky Way. In the constellation Circinus, where visible light observations see only a faint hourglass-shaped patch of black sky, Spitzer's dust-piercing eyes see more. Like a vision, a brilliant nebula resembling a graceful glowing spider teeming with clusters of massive young stars is revealed in this glimpse observation. The baby stars can be seen as specks of yellow at the center of the spider. Intense radiation and particle winds coming from the young stars creates the two bubbles that form the spider's shape. The process of star formation is at the core of this cosmic wonder, and glimpses revealed it in new detail. With millions upon millions of new stars to observe with this new vision, Glimpse will help address one of the vexing questions in astrophysics.
Well, believe it or not, the galaxy is full of stars. It's got about 100 billion stars. But in fact, nobody really understands how these stars are made. It's one of the great mysteries of modern astrophysics. And we have the hope that with the Glimpse data, we can in fact understand some of the process by which stars are made. There's a very complicated physics that's involved, and that's something that nobody's been able to do really in any direct way from observations, but I think Glimpse will be able to do that.
One way Glimpse will increase understanding of star formation is by studying dense star-forming regions in unprecedented detail. Peering deep into thick clouds of dust and stars in the plane of the galaxy, Glimpse explored a stormy region of star-forming activity about 11,000 light-years away in the constellation Sagittarius, revealing phases of stellar evolution from birth to their explosive demise. Through a dusting of blue foreground stars, Glimpse captured this view of thick, sooty clouds large enough to swallow dozens of solar systems. These clouds may harbor massive stars in the process of forming. This red star is 20 to 50 times as massive as our Sun. Below these clouds are colorful regions of less dense material that have been heated by stars and glow in infrared light visible only to Spitzer. Yellow and orange dots throughout the image are monstrous developing stars. At the other end of stellar evolution, this red ball is a supernova remnant, the remains of a massive star that died in a fiery blast. Astronomers think that the process of the supernova explosion, creating radiation, winds, and shock waves, may have played a role in forming the sinuous black dust cloud. These observations will ultimately help astronomers better understand how massive stars form, helping them to determine if the stars were born in the same way as our low-mass Sun or by another mechanism in which this stormy environment plays a large role. In other observations, with its penetrating vision, Spitzer has shown other star-forming wonders that will help us understand the many unanswered questions about star formation. Peering into the Carina Nebula some 10,000 light-years from Earth, Spitzer reveals never-before-seen details in immense clouds of dust that are heated by the massive star Eta Carinae, which rips at the clouds with winds and radiation. The shock from the blasting radiation winds forces gas and dust to clump together and collapse into new stars, which Spitzer reveals are buried in pillars of dust that are being blown away by Eta Carinae's winds. Looking closer yet at the Trifid Nebula, we first see the nebula as it appears in visible light. Then, using the array of Spitzer's vision, the Trifid takes on a new beauty and tells us more about its nature. The Trifid is unique because it is dominated by one massive central star, only 300,000 years old. This one family unit of a single massive star and the stars forming around it will add much to our understanding of the many ways that stars form. So, with Spitzer's unique, penetrating vision, The SINGS and GLIMPS programs have already advanced our understanding of our own Milky Way and other galaxies in our cosmic neighborhood. Old friends like M31, the Andromeda Galaxy, and M51, the Whirlpool Galaxy, are revealing new secrets to Spitzer's vision, while Spitzer reveals new beauty to us.